Hi, everyone. Thank you for coming to my talk today. So my talk is going to be on aerosol indirect effects on Cirrus cloud properties using a machine learning method based on global scale airborne observations. So my work is with Minghui Diao from the Department of Meteorology and Climate Science at San Jose State University. And I would also like to quickly thank my collaborators for their contribution to this project as well. And so jumping into the introduction, so we understand that cirrus clouds cover a large amount of the Earth's surface, up to 30%. And the microphysical properties of these cirrus clouds have the potential to respond to this rapidly changing climate. And so a few past studies that are related to my work found that climate models had weaker aerosol indirect effects. And this figure here in the top is from that study, which show aerosol concentrations restricted by temperature, color-coded by ice water content. And so in the observations here on the left, two panels, we definitely see that there's strong positive aerosol indirect effects. However, if you look at the right figure here, the nudge simulation output, we still see that positive trend. However, it's definitely much weaker than the observations. Another study found that cirrus clouds can be formed through two main pathways, either in situ or convective origin. And this is from Martina Kramer's 2016 study. And this figure shows where you can find these two types of cirrus clouds. Basically, in situ origin cirrus clouds are found in regions of slow updraft with low to medium ice water contents, and convective origins are more likely found in regions of fast updraft with medium to higher ice water contents. And so really we want to answer three main science questions in the study. Do small ice and large ice show differing AIEs? Do in situ and convective origin cirrus clouds show different AIEs? And how can we compare these aerosol effects with other effects like the thermodynamic and dynamic effects? And so going into the methodology of this study, so I used 5 NASA and 7 NSF campaigns, and the individual campaign flight tracks are shown in the global maps above. The ice number concentration and mean diameter are provided in the observational aircraft data. The ice water content is derived and calculated based on the mass diameter relationship with osmolality assumption based on the Brown and Francis method. And the relative humidity with respect to ice is calculated based on saturation vapor pressure with respect to ice. And since this is a cirrus cloud study, we restrict all the temperature data to less than or equal to -40 Celsius. And so just a quick overview of the instrumentation for each campaign. Basically, the most important difference in between the two agencies, NSF and NASA, is that the NSF operates the fast two-dimensional cloud probe, which has a measurement range of 62.5 to 3,200 microns, and the NASA campaigns use the 2DS probe, the two-dimensional stereo cloud probe, which has the capability of detecting small ice with a range of 5 to 3,005 microns. And so our initial analysis for looking at the thermodynamic and dynamic controlling factors on the ice microphysics found that each campaign had large variations in their microphysics. However, calculating a delta variable found that the second by second variations of each 1 degree Celsius bin for each data point were definitely much more comparable between the different campaigns. And so right now we're doing more work to reframe the definition of convective or in situ cirrus. However, so yeah, these results are kind of preliminary. However, for now, we're defining convective cirrus as plus or minus 5 minutes surrounding any 1 second vertical velocity occurrence of greater than 1 meter per second. And so in this figure below, we look at the ice microphysics restricted by RHI and vertical velocity in the second row, and also separated by convective and in situ cirrus. And so nothing too obviously sticks out that they're different between the two cloud types. However, we definitely see some higher NI in the convective cases for RHI and less fluctuations in the vertical velocity for the in situ cases. Now going on to the controlling factor, looking at the controlling factors of the aerosols, large aerosol Na500 and small aerosol Na100. So for the convective cases, we see that in the first row, similar structures to the last slide. We actually see indicated by the red circles, we see an overall increase in the IWC, NI, and DI for Na500 for the in situ cases. However, for the convective cases, we only see a slight increase right here where D log 10 Na500 is greater than 0. So this indicates that large aerosols are more influential on in situ cirrus clouds, which possibly indicate heterogeneous nucleation. For small aerosols, we see that there's a little bit of an increase indicated by the blue circles in the convective cases. However, for the in situ cases, we don't see any type of increase really at all in the average ice microphysics. So this indicates that they're more influential on convective clouds, indicating possible homogeneous nucleation. Excuse me. And so now we're looking at the aerosol indirect effects on small and large ice. So this is where we contrast the small and large ice. So we separated the small ice for analysis through a method of truncating the 2DS bins less than 65 microns. So this was shown on the left right here. The remaining bins greater than 65 microns would be combined with NSF 2DC data to create one large data set, which we analyze on the right-hand side right here. So the trends are overall pretty similar between small and large ice for IWC and NI with similar positive trends. However, we see this decrease in DI in the small ice that is labeled here by these red arrows. This decrease is actually observed in agreement with a recent study and review in ACPD that found that in the early and later growth phases of cirrus clouds, both homogeneous and heterogeneous nucleation occurred, which led to a decrease in small ice diameter and actually an increase in large ice diameter. So now getting into the machine learning part of this. So we investigated each individual variable that affects our outcomes individually, and now we can try to investigate these questions all together. So in order to set up this model, I use a decision tree algorithm to conduct 3 types of predictions. The first prediction is to predict in-cloud or clear sky occurrence. The second prediction would be to predict the fluctuations of ice water content. And the third prediction would be to predict the magnitude of ice water content. And as I mentioned before, we want to determine what affects our outcome, which we previously analyzed individually. And the next step would be to pre-process our data, which I use a listwise deletion method where I remove all instances when a NAN occurs, as this might cause trouble later when we try and split our training and create our training and testing data sets. And so in creating these training sets, I take random indices from the entire data set based on using a random function. And then I also get equal number of responses from both classes to keep this training bias to a minimum. So after all these restrictions, about 70% of the full data set is used for training, while anything not used for training would be considered in the testing set, which would be about 30%. And so getting into the results of these machine learning predictions. So the first prediction was, can we predict where cirrus clouds form? And the results showed that RHI is the most important factor among the 3 thermodynamic and dynamical factors. In other words, anytime the RHI was included as a predictor variable, we see the highest accuracy percentages. And also adding aerosol number concentrations also would improve the prediction results. And a general takeaway from here is that convective cirrus clouds usually had slightly lower accuracy indicated by the blue bar, while in situ cirrus clouds were more well represented by the in situ model with the higher accuracies. Second test, can we predict the fluctuations of ice water content inside a cirrus cloud? So here we see that larger aerosols, Na500, actually tend to have more impacts on in situ cirrus. And this is consistent with the previous slides that I showed before, which showed that large aerosols are more influential on situ cirrus. As you can see here, we see a higher accuracy. For small aerosols, once again, consistent with previous slides, we see a higher accuracy for convective cases for small aerosols. And overall, it is definitely much more difficult to predict the fluctuations of ice water content, as these percentages, accuracy percentage are like 60%, while before they're around like 80 to 90%. So the final test is predicting the magnitude of ice water content. And this test, we are basically these plots actually show the scatter plots of each individual prediction, the predicted on the y-axis and the true value on the x-axis, and anything that lies close to this 1-to-1 black line would be a perfect prediction. And so I found that basically when using a temperature model, ice water content is significantly overestimated by the model for lower RHI. As you can see, a higher density of the darker blue predictions above this 1-to-1 line. However, when you use a T, RH, and W model, it shows much more symmetrical predictions for all the thermodynamic and dynamical effects, which indicates that it's a much more well-represented model that covers all the impacts of T, RH, and W. So finally, just a quick summary. We wanted to create a global data set covering wide geographical regions, and we introduced a machine learning method to investigate these aerosol and depth effects. And we covered 4 main topics of small versus large ice, and we found that similar over positive trends in aerosol and depth effects for small and large ice, and there were some cases of decreasing DI with increasing aerosol concentrations. And for the convective versus in situ cirrus, we found that predicting convective clouds are much more difficult than in situ clouds, and the ice microphysical distributions for convective and in situ cases have a few differences. And the 3 types of machine learning predictions, we found that predicting in cloud and clear sky conditions have higher accuracy compared to predicting the fluctuations of ice water content. And predicting the magnitude of ice water content and NI are most difficult for the ML model. And finally, for the aerosol and depth effects, we found that large aerosols are more influential on in situ cirrus and small aerosols are more influential on convective origin cirrus. And with that, I'll stop there.